Hello and welcome to lesson 3, which is all about latent heat. Again, this is going to be split into two parts. The first part is going to be the theory of latent heat, and the second part is going to be looking at a practical method to determine the latent heat. Again, the practical is something we will do at school. So for now, we will just look at the theory so that you are equipped to answer any exam questions and have a better understanding of it. The first thing I would like you to do, though, is to read the following list of questions and to answer them. Some of them are a recap from last lesson, and some of them you will need to quickly search the answer on the internet. Please pause the video now and complete the 7 questions. Okay, so these questions were all chosen to either recap last lesson or to enhance your understanding. So particularly questions 6 and 7, for example, not on the A-level syllabus, but should enhance your understanding of the whole topic. So these are the answers. Pause the video now and mark your work. So we're going to move on to the theory of latent heat. Some of this is a recap of GCSE. Some of this will be an extension. So to start with, please pause the video and think through this question. Hopefully you should have come to the answer that at 100 degrees at atmospheric pressure, water will boil. It will start to change state. What this actually means in terms on a microscopic level is something you should also think through now. So what is actually happening when something reaches its boiling point? Well, the particles have been given so much kinetic energy because the temperature has been raised that they are vibrating. So, well, actually not vibrating, or vibrating and moving. Basically, they have enough kinetic energy to start to overcome the forces of attraction between them. So for water, this happens at 100 degrees Celsius at normal atmospheric pressure. An individual water particle, or water molecule, is moving with so much energy that the forces of the nearby molecules cannot keep it next to them, basically, and it has enough energy to leave the surface and move up into the atmosphere. So you should have seen diagrams like this before. So again, pause the video and really think through in detail what is happening at each stage. Hopefully you should remember that at 1, the temperature is increasing, the kinetic energy is increasing, and therefore the temperature is increasing. At point 2, the substance is changing state, it is melting. The temperature stays the same because bonds are being broken. The energy that is being put into the material or the substance is going into breaking the bonds, to separating the particles, not to change the temperature. Part 3, of course, the temperature is increasing. Part 4 is another state change where it's turning from a liquid into a gas. And finally, 5, temperature is once again increasing. At all of these stages, the internal energy is increasing. At stages 1, 3, and 5, the kinetic energy is increasing. At stage 2 and 4, the potential energy is increasing. So what do we actually mean by specific latent heat? Well, the specific latent heat is the energy required to change the state of a unit mass of liquid without a temperature change. Or Equally, the specific latent heat is the energy required to change the state of a unit mass of solid without a temperature change. And again, when it says unit mass, we just mean 1 kilogram. So there are two values for latent heat, and that's because there are two state changes. There is freezing or melting, whether you're adding energy or removing energy, and that's known as fusion. So we will talk about the latent heat of fusion. And there is also vaporization, which is when something is boiling or condensing. So we will talk about the latent heat of vaporization. So really, our definition should actually be changed. It should say the specific latent heat is the energy to change the state of a unit mass without a temperature change. And then more specifically, the specific latent heat of vaporization is the energy required to change the state of a unit mass of liquid to gas without a temperature change, for example. What I want you to do now is think about the following question. Which of these, so fusion or vaporization, has a greater value and why? Pause the video now and think through this question. The answer is that vaporization has a much greater value than fusion. It takes much more energy to boil a substance than it does to melt it. If you think about the particle model for solids, liquids, and gases, it should be fairly easy to think about why that is the case. To go from a solid to a liquid, we don't really need to change much about the configuration of the particles. Yes, they are going from nice, neat, ordered rows to freely moving past each other, but actually they're still very close together. And they certainly are confined to or confined by gravity on a table, for example. You don't see liquids or solids floating around. When we are going from a liquid to a gas, we are giving the particles enough energy to overcome not only their forces of attraction to each other, but to become completely free moving away from the rest of the substance. So a gas, the particles are much, much further apart and are no longer confined within a space. Unless, of course, you've got a gas inside a container. But even then, you're still increasing their kinetic energy so much that they are free to move anywhere very rapidly with a high energy. This also means that gases have a much, much higher volume than liquids or solids. It might be 10, 100 times as great a volume. So calculations with latent heat are pretty simple. Okay, we're always going to use the same equation. It doesn't matter whether it's for fusion or for vaporization. We're always going to use the same. Again, delta Q for change in heat, M for mass, and L for latent heat. The units of latent heat are joules per kilogram. And here are two values that are quite useful to remember. Again, you wouldn't have to remember them, but they're quite useful. For water, the latent heat of fusion is 334,000 joules per kilogram. And for vaporization, it's 2.3 times 10 to the 6 joules per kilogram. So you can see just how much greater the latent heat of vaporization is compared to the latent heat of fusion. I'd recommend that you pause the video now and just do a quick search on the internet for a table of values of other substances. So again, you can get a sense of how big these values are and how different fusion and vaporization are. Please pause the video again and complete the following two questions. Okay, question A. How much energy is needed to melt, bring to the boil, and boil away 0.5 kilograms of water? So there are 3 stages here, none of which are hard, but you have to do all 3 stages to complete the question. So stage 1, we need to work out how much energy is needed to melt the ice. And this is, of course, entirely separate from boiling and evaporating. So the calculation on screen. The second stage, we need to bring the water to the boil to increase its temperature. So we need to go back to the last lesson and we need to use the heat capacity equation. And finally, we now need to boil. So we need to again use the latent heat equation, but now with the value for vaporization. If we sum all 3 of those together, we get the final answer, which, as you can see, is a very high number. How long would this take a 2 kilowatt kettle? Not a particularly hard question. You, of course, need to use the idea that power is the rate of transfer of energy, and you get an answer which is approximately 13 minutes. I just want to show you this graph once again, because if it's been drawn properly, you will see that the line corresponding to melting or equally condensing is shorter than the latent heat of vaporization, so when it's boiling or condensing. And of course, that is also showing that it requires much more energy to boil something than it does to melt it. It's also worth taking a little bit of time to just really emphasize there is a difference between boiling and evaporation. Boiling is the state change from liquid to gas that happens at the boiling temperature, whereas evaporation is a physical process that can happen at any temperature. If you have a puddle of water on the floor outside, even on a cold day, it will evaporate. It will evaporate slowly, but it will evaporate. Evaporation is very useful because if we sweat, for example, it allows us to cool down. The most energetic molecules will leave the surface of our skin. They require energy to do so, and they will cool us down. But we would never think of that as our sweat boiling, because obviously we have not reached the boiling point of water. Boiling is something that happens at a very specific temperature. It's also worth highlighting that the boiling point or the melting point can be used to determine the purity of a substance. If we take pure water, it will always melt at 0 degrees Celsius, and it will always boil at 100 degrees Celsius. So if you have a substance that melts or boils at temperatures different to that, it cannot be water, or at least it cannot be pure water. If you add salt to water, it will change its melting point, its freezing point, and its boiling point as well. So we just have a few extra notes. I'll leave these on the screen for you to read. And again, I will give you a few seconds to pause the video and read these notes. Part 2, determining the specific heat, determining the specific latent heat of fusion for water. So I would like you to pause the video and think through all the steps that you would need to do in order to determine the latent heat of fusion for ice. Okay, it's a relatively simple experiment, but it's always useful for you to think through all the steps and also to think through why there are 2 beakers here and a control beaker. Hopefully you realize the control beaker is important because if you leave ice in a room, it will melt anyway. So you need to determine what effect you are having on the ice by using a heater and what effect the room is having. So you'll complete this experiment twice. And then the difference between the two beakers in terms of melted ice is what you've actually caused to happen. There are some other subtleties as well, like we want to ideally use crushed ice to try and reduce air gaps and increase the contact. We're going to need to top up the ice because we don't want the heater to be poking out the top. So please take a few seconds to read through this method. And also think through the measurements that you will take. Hopefully you've realized you of course need to work out the mass of the empty beaker first. Then you need to work out the mass of the beaker plus water, subtract it to get just the mass of the water. You also need to work out the difference between the two beakers, so you know exactly the mass of water that you have melted. The energy you've put in, of course, is current times potential difference times time. So now you can do energy divided by the mass of ice that you've melted due to the heater. That will give you the latent heat of water. We could, of course, do a similar experiment to work out the latent heat of vaporization of water. Please pause the video now and think through all the steps that you would need to take. Please read through the method, which is a pretty simple method, but should give you the correct idea. And that concludes the end of this lesson. The work that you should complete is on the Google Classroom. Thank you and goodbye.